Okay, let's take a really brief look at quantum numbers. Now remember, quantum numbers, for the level that we're studying quantum numbers, we're just going to think of them as four characteristic that describe or predict the possible location of an electron in an atom. Now we're going to remember things like no electron in an atom can have the same set of four quantum numbers, because a quantum number is kind of like an address, and there are really no two people with the same address. Oh, I know, you say there are more than one of you that lives at your house. Yes, but there's only one person that lives at your house that has your exact name. So there's really, just like there's no two people with the same address, there are no two electrons with the same address. So the first one of these numbers that describe or predict the location of an electron is the principal quantum number. Now the principal quantum number is abbreviated with an N, and it can have values like n equals 1, or 2, or 3, or 4, and so on. Now these quantum numbers describe how far the electron is from the nucleus. So n equals 1 is we often call this the energy level, and it's the period on the periodic table as well. So the n equals 1 energy level is closest to the nucleus, and as you get to higher numbers, you move further from the nucleus for those particular electrons that you're describing. And it also is the period on the periodic table, or the row on the periodic table. You remember that, of course. So the first period that contains hydrogen and helium, the highest electrons, if they're in their ground state, the highest electrons will be in the first energy level. And in the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, those are in the second period, and electrons are going to be filling up the second energy level on the periodic table. The second quantum number is the angular quantum number, and it's abbreviated with a lowercase l like this. And it is limited to values of 0 up to n minus 1. So if you're in the first energy level, you can only have L equals 0, because n equals 1 is n minus 1 is 0. If you're in the second energy level, you can have 2 values for L, and that would be 0 and minus 0 and plus 1, 0 and 1. Could be the possible values for the angular momentum quantum number. I'm missing a word here. That's why I'm struggling with this. Angular momentum quantum number. And it describes the shape of the orbital, and you can look that up and read more about it if you want, but for right now we're just going to move on. In the past, you may have called the angular momentum quantum number, we may have just referred to it as a sublevel, S, P, D, F, etc. Well, S is equal to 0, P is plus 1, D is 2, F is 3, and so on. The third quantum number is the magnetic quantum number, and it's abbreviated with a italicized or scripted M, and it can have values of negative L up through 0 and positive L. And it describes the orbital's orientation in space. Now remember, each orbital can have no more than 2 electrons in it. And when we sketched this in the past, you may remember that in the S sublevel, we sketched one circle and represented that as an orbital, and we said we can put one electron with this kind of spin and one electron with this kind of spin, and that represented our 2 electrons in the S sublevel. Now remember that value for L there would be 0. Now if we move to P, the value for P is 1, and so M can have values And then we're at the end of the first period. And as we move to the second period, the 3 electrons that are in lithium, they would be, 2 of them would be in the 1s sublevel, and then the next one would go into the 2s, and we would call that 2s1. And so as we fill, we can look at the periodic table and predict the location of the outermost electrons. As here the 2s electrons are filling, and then we're still in the second period, so now we're coming to the 2p electrons, 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. So that by the time we get to neon, which has 10 electrons, we have 1s2 and 2s2 and 2p6. And so we have those 10 electrons accounted for, 8 of them in the valence shell, and so the octet rule, which we find that if the s and p sublevels of the outer shell are filled, the atom is particularly stable. Now after 2p6, we come to sodium, which has just 1 more electron than neon, 11. So that 11th electron will go into 3s1. Then we'd have 3s2, 3p, 1, 2, 3, 4, 5, 6, and followed by 4s1, 4s2. But what comes after 4s? Well, after 4s, we come into the D block, but these are the D block of the 3rd energy level. And so these are going to end in 3D of some kind. Now within this block, there are some places where, for example, right here with copper, we're going to see, that's okay, here. I have a way of, let's see, where was I? I think I was talking about copper here. In copper, if we're looking at the 3d electrons of copper, and I'm looking here at the 5 orbitals that are in that 3d sublevel, remember Hund's rule says that these fill separately, and then as we continue across, so as we continue from 1, 2, 3, 4, 5, as we continue here, we start filling these in. And so we would expect that copper would look something like this, so that there would be a 4s with 2 electrons, and then the 3d would have 1 spot right there empty. Well, it turns out that it's much more stable if one of these electrons from the 4s level jumps out here and completely fills the 3d sublevel. So there are some exceptions to this building up process that we've looked at. Now the building up process that I've been describing here of going from 3d to 4p, that process is called the Aufbau process, building up 1 electron at a time and using that to predict where the element would be on the periodic table. So by the time we get to the end here, our outer shell electrons are 4s2 and 4p6, and the inner shell, see, this is on the 4th period down, that is krypton. But krypton is going to look a lot like argon, with the exception of these additional electrons, the 3d10 and the 4s2 and 4p6. So that's a brief summary of quantum numbers.
So I was working on the assignment.
Speak real loud so it'll record here for you.
Oh, no, this is an embarrassing question.